All right, let's dive into the wild world of chemical architecture. This is a place where a simple formula can be seriously deceiving, hiding multiple, completely different realities. We're talking about isomers.
So get this, take a look at these two molecules. On paper, they have the exact same parts list: 4 carbons, 10 hydrogens, and 1 oxygen, C4H10O. But that's pretty much where the similarities stop. One is a straight chain, the other is all branched out. They've got different boiling points, they react differently. I mean, they're entirely different substances, but they're built from the exact same atomic Legos. And that paradox, that's the heart and soul of isomerism.
So how in the world do we make sense of all this variety? Well, like any good explorer, we're going to need a map. We're going to use what chemists call the isomer family tree to help us navigate this world and see how these molecules can share a formula but lead totally different lives. Okay, so our map splits right down the middle into 2 main paths. Over on the left, you've got structural isomerism. This is where the fundamental connections between the atoms, the way they're actually linked together, are completely different. Think of it like you're totally rewriting the blueprint. Then, on the right, you have stereoisomerism. Now here, the connections are the same, but their arrangement in 3D space is different. It's the same blueprint, just built with a different spatial twist. So let's just lock in the official definition, so we're all on the same page. Isomerism is simply the phenomenon where 2 or more compounds have the exact same molecular formula. But, and this is the important part, they have different properties. That difference is key, and it all comes down to their structure. Let's start by heading down that first major branch of our family tree, structural isomers. We're about to see how this whole rebuilding the foundation thing actually works on an atomic level. And this visualizes the idea perfectly. Over on the left, you've got your shared inventory of atoms, basically your pile of building blocks. And on the right, you can see 3 completely unique structures built from that exact same pile. The whole idea is that the sequence of how those atoms are linked together gets completely rewritten. So our first type of structural isomers is called chain isomerism. For all 3 of these molecules, the formula is C5H12. But just look at the carbon skeleton. In pentane, we've got a nice straight continuous chain of 5 carbons. Then, in isopentane, the longest chain actually shrinks to 4 because 1 carbon is branched off. And then in neopentane, the main chain is down to just 3 carbons, with 2 branches sticking out. The skeleton itself has literally been shrunk and rebuilt. Next up, we've got position isomerism, and this one's a little more subtle. The core 3-carbon skeleton here stays exactly the same. The only thing that changes is the position of that functional group. In this case, it's the hydroxyl group, that OH you see highlighted. In propan-1-ol, it's hanging out on the first carbon, but in propan-2-ol, it is simply slid over to the second carbon. Same framework, just a different spot for the attachment. Now this is where things get really transformative. With functional group isomerism, the atoms literally rearrange themselves to form entirely different types of compounds. Both of these molecules are C3H6O, but the one on the left, propanone, is a ketone. See how the oxygen is double bonded to a middle carbon? On the right, we have propanal, an aldehyde, where that same group is now sitting at the end of the chain. This one simple shift puts them in completely different chemical families with totally distinct behaviors. They're true shapeshifters. And finally, there's metamerism. I want you to think of that central functional group, in this case the oxygen atom, as the center point of a seesaw. The game here is just to redistribute the carbon chains or alkyl groups on either side. So in methoxypropane, you have a 1-carbon chain on one side and a 3-carbon chain on the other. But in ethoxyethane, the balance is shifted. Now it's 2 carbons on each side. The functional group is identical, but the chains around it have just been rebalanced. All right, so we've seen how you can rebuild a molecule from the ground up, right? Now let's cross over to the other side of the family tree and explore stereoisomers. Because here, the blueprint stays the same, but the 3D reality gets twisted into entirely new forms. And the difference is laid out so clearly right here. The 2D structural view on the left tells you what's connected to what, but honestly, it doesn't tell the whole story. The 3D view on the right, that's where the action is. The bonds that look like wedges are coming out of the screen towards you, while the dashed ones are going back, into the screen. For stereoisomers, these 3D positions are what make all the difference. So, let's just make sure we've got this locked in. The crucial point for stereoisomers is that the atom-to-atom connections, what chemists call the constitution, are identical. The only difference is their orientation in 3D space. It might seem like a tiny distinction, but in the world of chemistry, it can change absolutely everything. Okay, so you come across 2 molecules. They've got the same formula.
How do you figure out what's going on? If they're structural isomers, how do you know which type? Well, let's get you set up with a simple diagnostic guide. Think of this matrix as your personal toolkit. For chain isomers, the rule is shrinking the skeleton. You're looking for a change in the main carbon chain's length. For position isomers, it's the slider. Some group has just moved its location. For functional, it's the shapeshifter. The entire functional group is transformed into something new. And for metamerism, it's shifting the balance. The carbon distribution around a central atom is different.
And here's exactly how you use the kit. It's a simple step-by-step process. First things first, always check if the functional group itself has changed. If it has, boom, you found functional isomers. If not, okay, move on. Check the length of the main carbon chain. If that's different, you've got chain isomers. And if the chain is still the same, then you're looking at a more subtle shift. Either a group has just moved its position, or the carbon chains have been redistributed around a central atom. It's really just a simple process of elimination. And that kind of brings us to our final thought. Isomerism really shows us that a finite set of building blocks can lead to an incredible, almost unbelievable diversity of structures and functions. It's a fundamental principle of how complexity works. So it leaves you with a question, right? If just a handful of atoms can create this much variety simply by rearranging themselves, what other hidden realities are just waiting to be built from the simple ingredients all around us?